Welcome to video 2 from your electrochemistry unit. We're going to talk about voltaic cells, also known as galvanic cells. So, you have probably used batteries in your lifetime, which means that you have used a voltaic or galvanic cell. They're defined as a device that transfers electrons from one reactant to another through a pathway. These guys have to be spontaneous in order to be useful at all. They are always spontaneous. So you want to know that. If they're not spontaneous, then it'll be something else that we have to put energy or work or something into in order to make it actually do anything. So remember, if something's spontaneous, it just kind of does what it does all on its own. Gives free energy less than zero. Chemical energy in these cells is converted to electrical energy that moves electrons through a wire. In these guys, it's kind of special because the reacting species, they actually don't even have to touch each other in order for the reaction to happen. In order for the oxidation and reduction to occur, they don't have to touch one another. These guys are used to perform electrical work, create a flow of electrons, power your calculators, power, I don't know, your blender. Are blenders battery operated? No, I don't know, anything. Battery operated things. So, here's an example of an oxidation reduction reaction. Here we have zinc losing electrons and copper gaining electrons. So go ahead and refresh your memory. Which one of these is oxidation, which one is reduction, and which one is the oxidation agent, and which one is the reduction agent? Figure that out. All right, and hopefully you paused and did that. If not, pause now. So the one that lost electrons, let's see, I like to use oil rig. You could also use Leo says Gur. This is oxidation, which is the reducing agent. This one was reduced, which was the oxidation agent. Cool. All right. So here's an image of a galvanic cell. So we have two different beakers. They have two different solutions in them. On this side, we have the zinc half reaction occurring. On the other side, we have the copper half reaction occurring. You can see that we have solid zinc over here, and what ends up happening is that solid zinc loses electrons. These electrons are transferred through this wire. And when it loses those electrons, then we have zinc ions that pop off, and the solid slowly disintegrates. Basically, the zinc falls off of it as an ion. We have these nitrate ions that are also in solution. They are not affecting the reaction. They're just kind of there to make sure it stays neutral. Positives and negatives, we want them to cancel out. So those electrons come off of the zinc, they fly through this wire, they go through the voltmeter, we read, oh look, electrons are flying through, and they keep on moving until they hit the cathode, which is made of copper. And what ends up happening is those extra electrons allow these copper ions that are in solution to gain electrons and become solid copper. So what we're actually doing is we're building up this bar over here. So this one is getting eaten away. So it's getting smaller and smaller, and the other one is getting larger and larger. We also have something over here called a salt bridge, which I will go over. Oh, if you heard that, that was my cat saying hi. We have a salt bridge. What else can we label? We'd also want to be able to label which side is the positive side, which side is the negative side. The anode is the negative side. Anode is kind of like anion, so that might help you remember. The cathode is the positive side. If you have problems remembering which is positive between anions and cations, here, let's write those words out. Anions are negative, cations are positive, and what I like to say is, oh, cations are positive because they have a plus sign in the middle of the word. Pretty cool, right? So you want to be able to identify which side is the negative side, which side is the positive side. The anode is involved with the negative side, like anions. All right, so now that we have a basic overview of a galvanic or voltaic cell, let's look at this drawing. So this could be something that you might have to do. So be able to draw these. In fact, our video is going to culminate with you drawing one of these. So I'm going to, let's see, I'm going to pick a color that's not on this slide. How about, I don't know, this slide has a lot of colors. Purple. And I'm going to put a star next to everything that you need to be able to label. You need to be able to label where the half reactions occur. So you need to show zinc on this side, copper on that side. You need to be able to label the anode and the cathode. You need to be able to label which side is negative, which side is positive. You need to show the flow of electrons, just like this. My cat's throwing a fit, sorry about that. And you also need to be able to label the flow of these ions within the salt bridge. So notice how we have this little thing, it's called a salt bridge. And it shows that this cation, see this is a cation here, is going to flow towards the cathode. And the anion will flow towards the anode. What else? I believe that is everything. So you need to be able to label everything that I kind of put a purple marker around. So let's go over these different pieces in more detail, and then we'll try a problem out. So you want to know what a half cell is. So a half cell would be one of the compartments of a voltaic cell. So we know it's got these two different compartments, right? So here is the half cell, there's another half cell. The anode is the electrode where oxidation occurs. So usually the anode is written over on this side, and that's where oxidation happens. And then the cathode is where reduction happens, and that's usually shown on this side. It doesn't matter which side you put it on, but if you always do it in the same exact way every single time, it might help you keep everything straight. If you have trouble remembering, does anode go with oxidation or reduction? Does cathode go with oxidation or reduction? My trick is red cat. I did not come up with this, somebody else did, but reduction happens at the cathode. You could imagine a red cat, happy little red cat, meowing in the background just like mine. Okay, reduction happens at the cathode. So I can write that over here. So what you do is you'd write the half reactions down here. Half reaction. All right, and then electrodes are often made of a conducting material like platinum or graphite, and they serve as the surface for electrons to be transferred on. So that's that little wire that comes through here. And then you might have heard me mention the phrase salt bridge, just like, 30 seconds ago. Let's talk about that. The salt bridge allows the migration of ions that maintains electrical neutrality of the solutions. So let's go back. Electrical neutrality. So you know how we're getting more and more zinc. We're getting more and more zinc over here as those electrons go away and leave zinc ions behind. So this becomes more and more and more and more positive. We need these ions from the salt bridge to gather down here to cancel out the positive charges coming from the anode. And then the same thing happens over here. So here we are losing positive charges as these ions become a solid, and so the positive charges from the cation and the salt bridge will show up over here, and they will try to put that back in there. We want to add up more positives to cancel out the negatives that were already in solution. So the point of a salt bridge is to maintain electrical neutrality. They are U-shaped, so you'll see them, like if we have our two different beakers, it'll usually be something like this, with the wire going above and around it. So this blue tube here is our salt bridge. This. They have anions and cations within them. The anions will always migrate towards the anode. The cations will always migrate towards the cathode, so that's pretty easy to remember. And they're going to contain some sort of electrolyte solution, so something that dissociates into ions, and they need to be not involved in the reaction, so things that will not affect our reaction. Sodium and nitrate are good examples of that. Sulfate is also used pretty often. Yeah, so for example, when zinc is oxidized, like I was saying before, we get more and more positives over here, more and more positives. So what will happen is nitrate, which is negative, will go through the salt bridge and be like, I'm here to save the day. And they will add more negatives to cancel out those positives that the zincs are adding. And then copper over on the other end will be reduced, which means we're actually going to lose some of our positive charges. We won't have very much. We'll just have, not as much. And so sodium will come on down from that salt bridge and be like, I'm here to save the day. And it will add in more positives to balance out whatever negatives were already in that solution. If the solutions don't remain neutral, then the reaction is just going to stop, and that's not good. We want our batteries to keep going, right? So the reaction will stop if it does not remain neutral. That would be because if, for instance, in the cathode, if we have an overall negative charge in here, then these electrons that are trying to come in would be repelled. They go, oh no, there are already a whole bunch of electrons in here, and they would just kind of go back. And that's not good. We want the flow of electrons to continue on forever and ever. Okay, so what if the ions in the salt bridge do react with one of the half cells? Well, that wouldn't be good because a solid precipitate would form. And if that happened and those ions start bonding with other ions, then we no longer have a solid electrode that things can really react with. That electrode, that solid electrode, needs ions to react with it. So we don't want this to happen. If that happens, then fewer electrons can be transferred, and then, the life of the cell is reduced, the voltage is lowered more quickly, and, if we removed that salt bridge and the electrical neutrality is not maintained, then the reaction would just stop immediately. We'd have 0 voltage. No good. So here's an even more visual version of this happening. We have our zinc, the anode, which is where oxidation occurs. Electrons are leaving it through this wire over here. And as those electrons leave, zinc comes out. We get more and more zinc, and the solution gets more and more positive. And so the salt bridge supplies us with some sulfate to balance out those positive charges. Then over here, copper, we are building up our copper electrode over here, and we are gaining more and more of the solid, which means we're losing these positives. They're going away, right? And so in order to balance out that lack of positives, sodium comes in to save the day and says, hey, I'm positive, and it balances out those negatives that were already present from the sulfate that was in that solution. Cool. All right. So now we're going to go into a practice problem. Oh boy. So the oxidation reduction reaction is spontaneous. A solution containing potassium dichromate and sulfuric acid is poured into one beaker, and a solution of potassium iodide is poured into another. A salt bridge is used to join the beakers. A metallic conductor that will not react with either solution is suspended in each solution, and the two conductors are connected with wires through a voltmeter or some other device to detect an electrical current. The resultant voltaic cell generates an electrical current. Indicate the reaction occurring at the anode, cathode, the direction of electron migration, the direction of ion migration, and the signs of the electrodes. So this could be an FRQ. This could show up on your FRQ. So if you are adventurous, go ahead and try this without me. You're going to try to draw one of these guys and label everything that it asks for. In order to label this, you need to know the two different half reactions. So on this next slide, I'm going to go ahead and do this problem. So go ahead and keep that slide in front of you while I'm doing this. I'm going to draw my two different beakers. I'm going to decide that I'll put my, I'm going to put oxidation on my left side over here, and I'll put reduction over here, just because I like to always write them like that. What you'd need to do is look at the equation back here and figure out what is being oxidized and what's being reduced. So, let's see. Right now, chromium is jumping out at me, and iodine. So what you'd want to do is write out their half reactions. You should try this without me. I'm just going to go ahead and write the answer now if you don't pause. Okay, so I'm going to put my iodine half reaction here because I saw that iodine is being oxidized. And I can see that this guy right here went from a charge of 6 plus to 3 plus. All right. What else? I want to label the anode and the cathode. Well, I need to get my strips in here. So there's this one, and here's that one. I want them to be connected by a wire. Here's that. All right. So I know that I've got my red cat phrase. So red cat, reduction, cathode. This is my cathode, which means that this guy over here is positive, which means this one must be negative. This is my anode. I'm kind of talking out my thinking to you as I go. This is what you would need to be showing on your test. Anything that's in red is an answer. Okay, what else? I need to show the flow of electrons. So electrons are flowing from the anode to the cathode. So I could say like this, electrons flowing that way, something that shows which way electrons flow. What else do I need to show? Let me check some stuff off. The reaction occurring at the anode and the cathode, those are my half reactions. I did those. I showed the direction of the electron migration. I showed the signs of the electrodes. Now I need to show the direction of ion migration within the salt bridge. So I'll draw a salt bridge to help myself out. Let's get a new color for that. So, salt bridge. I want room so I can actually write ions in there. Okay, and I have to come up with some ions for my salt bridge. I'm going to pick something that is soluble with everything. I know that sodium is soluble in everything, so I have Na+, and I also have, I know, nitrate. I believe nitrate is soluble with everything as well. If not, it's very soluble in general. So now I'm going to show which way these guys migrate. All right, well, I know that my cation is going to migrate towards my cathode. So I'm going to show an arrow saying this is going to go that way. And I know that my anion is going to migrate towards the anode. So loop, there it is. And that's it. It's not pretty, but it works. It's not pretty, but it works. So that would be my answer. So that is the end of our second electrochemistry video.